Hello students, how are you all? I hope you are doing absolutely well. So, we were on the last chapter of the class 10th chemistry, that is periodic classification of the elements, and until now we have discussed about a lot of terms in this periodic table chapter. Firstly, we have gone through some of the early attempts that is done by Daubernier, Newland and Mendeleev, and finally that modern periodic table has been accepted worldwide, whose concept has been given by Moseley. Now, we are looking for some of the trends in the periodic table, that how the basic properties and how the basic trends are going to be changed in the periodic table. So until now we have discussed about the valence electrons and the valency in the periodic table. Later on we have gone through the topic that what are the atomic radiuses variation in the periodic table. So previously we have discussed about the covalent radius. It is actually the half of the internuclear distance between the two atoms, and these two atoms are bonded to each other and formed by the overlapping, and covalent radius generally found in the case of known metals only. Now let us move to our second type of the radius, and the second radius we have is about van der Waals radius. Now, what actually the van der Waals radius is? The van der Waals radius is actually the half of the internuclear distance between the two isolated atoms, or it may be defined as a half of the internuclear distance between the two atoms, between the two adjacent atoms of the neighboring molecule. So, here is the definition of the van der Waals radius. Firstly, we can say that it is half of internuclear distance between two isolated atoms. Isolated means they are separated atoms. So, this may be the isolated atoms. So, how can we consider the internuclear distance? Suppose I am considering two isolated atoms here. These are two isolated atoms. This is the nucleus part of these isolated atoms, and I am denoting these nucleus parts as X and X. Now this distance from center to center, this is internuclear distance, and the half of this distance is known as van der Waals radius. So we can say that radius, that is van der Waals, is given by half of EAB. EAB is what? EAB is actually the internuclear distance between two such kind of the atoms, and you can see that these are two separately isolated atoms. So this is the one form of the van der Waals radius we can consider. Now let us move to the another definition of the van der Waals radius. Van der Waals radius is actually defined as a half of the internuclear distance between the two adjacent atoms of the neighboring molecule in the same element. So we can say that it is also defined as half of internuclear distance between two neighboring adjacent atoms of neighboring molecule. We have to consider adjacent atoms. Adjacent atoms of neighboring molecule of an element. Now, this is defined as the internuclear distance between the two adjacent atoms of the neighboring molecule. Now, how can we consider the neighboring molecule? Suppose we are having a structure. Now you can see that here I have drawn the atoms, and we can see that these are the two adjacent atoms, and the two adjacent atoms of the neighboring molecule is forming a internuclear distance, and half of that distance is actually the van der Waals radius. So how can we mention the van der Waals radius here? It is the half of the distance between two adjacent atoms in the neighboring molecule. So we can say that it is actually the van der Waals radius, and I am writing here AB. So according to it, R van der Waals will be equal to half AB in case of adjacent molecules. So this is in accordance with the isolated atom when the two atoms are completely isolated from each other, but it is the half of the internuclear distance between the two adjacent atoms in a neighboring molecule only. So you can see that these are the two adjacent atoms, and what we are doing the half of the internuclear distance here. So it is about the van der Waals radius. Now what will happen actually, in case of helium, we have a van der Waals radius that is equal to 1.20 Armstrong. So we can write here van der Waals radius for helium is 1.20 Armstrong. Now, covalent radius that we have discussed earlier, that is usually found in non-metals, is generally very small as compared to the van der Waals radius. This actually happens because the van der Waals radius is considered only in the cases of group 18 elements, which are known as the zero element, because the zero elements do not have a tendency to form the chemical bonds. So generally the 18th group element, that is known as the zero group element, they usually show the van der Waals radius. So for the gases like helium, neon, argon, krypton and xenon, we have to consider the van der Waals radius only. So we have found that the covalent radius is very small as compared to the van der Waals radius. So we can write here R covalent is less than R van der Waals. Why covalent radius is smaller than the van der Waals radius? Because covalent radius is actually formed by the overlapping of the two bonded electrons. But you can see that it is not formed by the overlapping. Because of the overlapping, the size of the atom will contract, or we can say that the size of the atom will going to be reduced. So we can say that this is the important one, that covalent radius will be less than the van der Waals radius. This is because covalent bond is formed by overlapping. Covalent bond is actually formed by overlapping. So the overlapping of the bonded molecules, so the bonded molecules will have a less radius as compared to the non-bonded one. So covalent radius is smaller than the van der Waals radius. Now one more discussion we have done here, the group 18 elements which have the zero valency is going to exhibit the van der Waals radius. So one more point here, I am writing it here. Van der Waals radius is considered for group 18 elements. Group 18 elements generally going to show the van der Waals radius. So this is about the van der Waals radius we have discussed here. Now the third category of the radius we have to discuss is about the metallic radius. So let's move to the metallic radius. Just copy this from here so it may be easier to learn their definitions. Now let's move to our next topic, which is about metallic radius. So our next topic is all about metallic radius. So now, what actually is the metallic radius? Metallic radius may be defined as the half of the internuclear distance between the two atoms in a metal lattice. So if we are considering metallic radius, it is found only in the case of the metal, as the name indicates. So we have a definition here. It is defined as half of internuclear distance between two atoms in a metal lattice. So this is the definition for metallic radius. Now let's see the diagrammatic representation that how metallic radius can be considered. Suppose I am considering two atoms of the metal here. These are two isolated atoms. Again we have the nucleus here. This is the nucleus, and this is known as the internuclear separation, or we can say the internuclear distance. If I am giving this name as E and F, so the R metallic, that is the metallic radius, is equal to half of the internuclear distance between the two metals or the two atoms in a metal lattice. So among all the radius, you have considered that it is actually the half of the internuclear distance. But what actually changes here? In metallic radius, we have to consider the metals. In case of the van der Waals radius, we have to consider the adjacent atoms. And in case of the covalent radius, we have to consider the bonded atoms. So these are the simple minor differences, but they are of the great consideration. So you can see that internuclear distance is a major part for calculating the radius. Now, metallic radius is again generally greater than the covalent radius. So we can say that R metallic will be greater than R covalent. So metallic radius will be greater than covalent radius. Now we can see that if we want to know the trend in the case of these three radius, we can say that what trend they are going to follow. The trend they are going to follow is that R van der Waals is greater than R metallic is greater than R covalent. It means if you consider all the three radiuses, the van der Waals radius is actually found to be much greater than these two. And you can see that the covalent radius will be found to be very small. So this is about all the three radiuses we have discussed. Now let's move to the fourth category, that is about the ionic radius. Now what actually the ionic radius is? Ionic radius is defined as a distance between the nucleus and the ion that is present in the outermost shell of an electron, or we can say that it is defined as a distance between the nucleus and how the nucleus have its control on the electron cloud. It means how will it going to affect the last electron cloud in the nucleus. So let's move to our next topic, that is about ionic radius. So now let's move to our next category, that is about the ionic radius. Before starting the ionic radius, let's have a look at this, how the covalent and the van der Waals radii is going to change in the periodic table. So, this is the table which is going to show us the covalent radii, and you can see that the value of the covalent radii is very less, and if we move from left to right in the periodic table, it compressively decreases in the periodic table. You can see the decreasing trend here. Firstly, it is 1.54 for sodium and it is going to be 1.04 or 1.14. It means in going along the period, the covalent radii is going to be decreased. Now, let us have a look at the van der Waals radii. This is the tabular description of the van der Waals radii. As I have told you that the van der Waals radii is considered only for the group L18 elements. This is considered for group 18 elements, and the group L18 elements will exhibit the van der Waals radii, and you can see that the values of the van der Waals radii is very large, and it is usually expressed in Armstrong. So this is the curve for, this is the tabular description for the van der Waals radius we have discussed yet. Now let's move to the next topic, that is about the ionic radii. Now, what is ionic radius? Ionic radius, as the name indicates, it is defined as the distance between the nucleus and the ion that is present in the outermost shell of an atom. So, we can say that it is the distance between nucleus and ion present in the outermost shell. Or in other words, we can also say that ionic radius is defined as a distance up to which nucleus has its control over the electron cloud. It means nucleus is going to control the electron cloud. So, up to how much distance that nucleus is going to control the electronic cloud is known as the ionic radius. So, we can say that it is defined as a distance up to which nucleus exert force on electron cloud. It means nucleus until controls the electronic cloud, it is defined as a distance and it is known as the ionic radius. So, it is quite simple that ionic radius will be considered in the cases of ions only. So, we can say that we have basically two types of the ions, that is cations and anions. So, we can say that we have two types of ions. Ions are of two types, and these ions are cations and anions. Now, what are cations? Cations are actually the positively charged ions, and anions are actually the negatively charged ions. So, we can say that cations are positively charged and anions are negatively charged ions. Now, the size of the cation will always be smaller than the parent atom. Why this is happening? Because in the case of cation that is formed by the positively charged, it means it is formed by losing something. So if it is going to lose something, it will lose the outermost electron, so the size will compact easily. But on the other hand, the size of the anion will always be greater than the parent atom, because anion are formed by taking an electron. So the size will automatically going to expand. It means its electron cloud will be expanded. So we can say that two more conclusions from here. Size of cation is smaller than parent atom, and the second conclusion we can draw on from here will be size of anion is greater than parent atom. So these are the 2 points that we have concluded, that size of the cation will be smaller than the parent atom and the size of the anion will be greater than the parent atom. Now the next point that we can conclude from here will be about the isoelectronic species. Now the word iso means same and electronic means they have the same number of electrons but the different value of the nuclear charge. So let's move to our next category. We are going to discuss about isoelectronic species. Now what are these isoelectronic species? Isoelectronic species are defined as the species which have same number of electrons. These have same number of electrons, but what thing is different? They have the different value of nuclear charge. Same number of electrons but different value of nuclear charge. So these are the two things about isoelectronic species. Now let's consider some of the isoelectronic species and what trend they are following in the case of ionic radius. Let's see here. Now if I am considering some of the species as I am writing here, suppose we have S2 minus, second we have, after sulfur we have chlorine, after chlorine we have 17, 18 and it is for potassium, potassium is 18 and again 16 plus 2, 18, chlorine 1, 17 plus 1 and 18 is for argon. After potassium we have calcium. So these are some of the isoelectronic species I have considered. Now why they are called the isoelectronic species, you can see from here. Sulfur having atomic number 16 plus 2 is having 18 electrons. Chlorine atomic number 17 plus 1, again it will have 18 electrons. Potassium 19 plus 1 means 18 electrons. Calcium again 20 plus 2. 20 plus 2 means it is able to give 2 electrons, again 18 electrons. So you can see here the number of electrons in such cases are same. You can see from here the number of electrons in this case are actually same. So if the number of electrons same, if number of electrons are same, we can say that these species are isoelectronic species. These are isoelectronic species. Now, these isoelectronic species you can see having a same number of electrons. But what about their nuclear charge? Their nuclear charge is plus 15, plus 16, plus 17, plus 19 and plus 20 respectively. So you can see that the isoelectronic species is having the same number of electrons. It means the number of electrons are same, but what you can observe from here, the nuclear charge is plus 15, plus 17, plus 19 and plus 20. So we can say that these species are actually the isoelectronic species. So how the ionic radius in case of the isoelectronic species will follow the trend, let's see now. But before that, copy this from here. So now let us see a trend in case of ionic radii. Suppose we are starting from nitrogen. If I am considering N3 minus, O2 minus, nitrogen, oxygen. After nitrogen and oxygen, which element will come? We will not take neon and neon because it is a counted in the group 18 elements. We have fluorine, that is F plus. After F plus, we are going to take sodium. Then we have potassium. After potassium, we have sodium, after that magnesium. This will be Na plus, Mg plus 2 and that aluminium. Now which elements I have considered? Starting from atomic number 7, 8 and 9, we have left 10. Why neon we have left? Because neon is counted in the group 18 elements. Then we have considered 11, 12 and 13. So now simultaneously I am writing the atomic numbers here. We are writing atomic number here. So the atomic number for nitrogen will be 7, oxygen 8, this is 9, and what about this sodium? It is 11, it is 12 and it is 13. Now let us calculate the number of electrons in each case. These are the atomic numbers. Now we are calculating the number of electrons in each case. So the number of electrons will be, you can count from here, 7 atomic number for nitrogen and it is able to gain 3 more electrons. So 10, 8 plus 2, 10, 9, fluorine is negative. So it is F negative. 9 plus 1, 10, 11 minus 1, 10, 12 minus 2, 10 and 13 minus 3, 10. So you can observe that the number of electrons for each species here is 10. So we can consider that these are isoelectronic species. But what about the case of trend of ionic radius in such compounds? You can observe that number of electrons are same. Number of electrons are same. The number of electrons are same, but what will be the trend for ionic radii in such case? So we know that if we are moving from left to right in the periodic table, the atomic radii will going to be decrease. So aluminium, that is Al plus 3, this is the element which come in the right side of the periodic table. So in moving from left to right, the atomic radii is going to be decreased. So same trend will be followed by the ionic radii because the effective nuclear charge is going to be increased. So we can say that what will be the trend in atomic radius or ionic radius? The trend of ionic radius will be Al plus 3 smallest, then Mg plus 2, then Na positive, then F negative, then O2 negative, then N3 negative. So this will be the trend of the ionic radius in case of the isoelectronic species. Now what we have observed from here, among all these isoelectronic species, the largest ionic radius will be of the N3 minus. It means nitrogen will going to have a highest ionic radius. So this is about the trend of ionic radius in isoelectronic species. Now let us have a look at the tabular description that how these ionic radius will vary along the period and along the group. So now we will see the tabular description here. So you can see that this is the trend in case of the ionic radii. Now what we have observed from this table, you can see that lithium is having an atomic radii 1.52. But if lithium is going to form the cation, that is Li plus, its size has been reduced to 0.59. It means the size of the cation will be always less than the parent atom. So this conclusion we have already discussed, that size of cation will be smaller than parent atom. Now let us consider one more example here. Suppose I am taking aluminium here. In case of the aluminium, what we have observed that its atomic radii is 1.43. If aluminium is going to form cation by losing 3 electrons, we can see that the size reduced to 0.50. So this trend shows that after forming cation, the size of the cation will be smaller than the parent atom, and after forming an ion, the size will be greater. So this is the trend of ionic radii in the tabular form. So this is all about the trend in the ionic radii we have seen here. So this trend has been completed. We will discuss many more terms in our next lecture. Thank you so much and have a nice day.